Hello and welcome to the second lesson here on the wave nature of light. Today we're talking about two popular theories that existed and the ramifications and how they were interpreted and so on and so forth. So we're going to talk about the corpuscular theory. Now, if you have heard of this, you've probably heard of it. Corpuscular basically means particle. So the particle theory of light versus the wave theory of light. And who are the parties involved here? Well, we have Newton and his supporters, and then we have everyone else in the world. So it's kind of an interesting story as we move our way through. So today's goal, I want you to be able to explain and identify be able to explain both sides of the physics debate over the wave nature of light. All right. So what do we got to start with here? Let's do a little bit of a history lesson before we get into the actual argument. So how does light travel? So back, we talked about in the past that scientists were really philosophers for the most part back in the good old days. And Plato, with the Greeks, he believed or postulated that light was streamers that the eye emitted. So he believed light came from your eye, and when the streamer from your eye struck an object, you were able to see it. Okay, so basically your eye was sending out basically waves, and when your wave struck something, you're able to detect it, kind of like sonar. Then the Greeks, they were our major movers and shakers in terms of science in that era. Pythagoras believed that light traveled as a stream of fast-moving particles. So he postulated that light consisted of particles that were moving at an extremely high speed and shooting from the source. Then we get into some of the other Greeks, and they started to postulate that light was more like a wave. So all of a sudden, the Greeks have created two significantly different belief systems in how light worked. So finally, the controversy, it really came to a head during the 17th century, and the two main people involved here was Newton and the particle theory, and his major supporter was a French physicist named Laplace. And on the other side of the table was Christian Huygens, and he believed the wave theory, and supporters of him were Robert Hooke, we talked about in earlier unit, and he was our president of the Royal Society, so he was kind of the head honcho that kind of dictated which science theories were correct and which weren't, or which were acceptable and which weren't. The problem arose that Newton had so much power and so much pull back then because, as I mentioned in class, he did the one summer that he had to stay home because of the plague. He came up with calculus. He came up with his theories, basic theories of physics, or Newton's laws, his three laws, and he came up with some planetary mechanics all during the summer. So I mean, those are three huge changes to the science world. So when Newton comes out and says something, people kind of sit up and listen, regardless the evidence provided. So if you can imagine, gentlemen with glasses and lab coats with kind of chalk brushes throwing back and forth, the battles got significantly more and more intense as time went on. So let's talk about some of the arguments that were made here, so you can have an idea of the frustration for the people that were promoting the wave theory of light. So rectilinear propagation is one of the properties of light, and it simply is shadows are created because light travels in straight lines. So we have our two camps here. So we have waves, and this should be on the other side. This is particles. So we already just talked about this in a previous lesson, that why do we have shadows? Well, if I have a barrier and I have wave approaching and light approaching as a wave, that the waves will pass around the object like water waves, and if we have a wall in the back, it creates a shadow. So they said, well, obviously it shows we can put this look at it in a pool, you put a barrier in, it produces a shadow. Newton said, well, that's not correct, because you know what? If light travels as particles, then these particles, when they strike the barrier, will stop, but the particles that get by the barrier are going to strike the wall behind, and in the same fashion, we'll create that same shadow. Which makes sense, because if you think of kind of throwing a tennis ball machine, throwing tennis balls at a wall, some getting by, you're going to have a region behind that wall that is never struck by tennis balls. So that could be the same as shadow being cast on a wall. So we see here, to start off with, the debate in this particular topic is kind of sort of balanced, because one is equally believable as the next. So next we move on to diffraction, and that is the concept that light bends when it passes through an aperture. So particles. My PDF kind of messed up on me here, or my note. So diffraction, light bends when it passes through an aperture. So that's like a single slit. So we talked about this, and we investigated this in the 3U course. So when light waves strike a barrier with a hole in it, and you can show this with the water table, and that's what the wave theory scientists were able to physically show it. They showed that the water then spread out like this. Now, Newton didn't have these cool hands-on things, because the wave theory people, or the wave theory scientists, Huygens, he actually had a water table. He could actually demonstrate this property. Whereas Newton simply dismissed it and said, no. What's happening is that the particles, there's billions and billions of particles that are trying to get through this hole. So it's kind of like trying to take the class and try to jam everyone out the door as fast as we can. So if we lined everyone up in the room, put them right at the door, and then pushed from behind and spit everyone out, what would happen is all these collisions that are happening in this region right here would result in people bouncing out in all directions. Okay, so collisions from the particles, collisions from the particles at the slit. Oops. At the slit cause the dispersion pattern. And not overly scientific, he's just sort of making this up on the fly, countering the argument, because he has no real evidence. He can't actually see these particles. Oops, one sentence is actually done. All right. So again, technically it comes to a draw, because one theory is being demonstrated, the other one Newton is saying, so Newton can't be wrong. When would Newton ever be wrong? So then we talked about reflection, or they moved on to the topic of reflection. So reflection, this one was actually one that Newton could easily demonstrate. And I already talked about this again in the review for 3U. We know that waves that strike a surface will in fact reflect such that the angle of incidence equals the angle of reflection. And again, Huygens could demonstrate this inside a water tub. Newton could also demonstrate this by simply taking a ball or whatever object he could find, and if you fire a particle, or for us, let's use a tennis ball for example, at a wall, it's going to bounce off such that this angle is equal to this angle. So that angle of incidence is equal to that angle of reflection. So something that's simple to show. So I is equal to theta r. All right, and not only that, to further Newton's cause here is that he could actually show it mathematically using his physics formulas that he developed. Vx, Vy, and you can then calculate Vx, Vy, and he uses kinematics formulas that would also support the evidence mathematically. All right. Moving along then, we move into refraction. So refraction is when light bends when it goes from one medium to the next. So we talked about this in the previous video. We did an investigation with Snell's law. I'm going to simplify it down. But if we go from, I'm going to stick with deep and shallow. Well, we did go through Snell's law, so let's talk about air and water. So let's go from air to water. So less dense to more dense. So our initial light ray would strike here. It would enter a more dense medium. So it's going to bend toward our center line. All right. So that theta I and theta, okay, will support, so theta I in this case is going to be bigger than theta R for refraction here. And we can show, and again, to Huygens' benefit or credit, Snell's law supported him completely. Whereas Newton actually did something that, did something that goes against, or his explanation is probably his weakest explanation coming. The only way that Newton could postulate this happening was that he used the example of a ramp. So I'm going to try to draw kind of a 3D ramp here. So there's the flat section. It goes down on a slope and it returns to a flat section. So we are going to send this particle down the ramp. Down the middle of the ramp, I'm going to draw a center line. So he said that a light particle traveling along, entering into, from air to water again, so that he's saying up here air, he says down here water, same example as Huygens. If you go down the ramp, the particle is going to actually speed up, which means it's going to bend towards the center line. All right, so we're measuring, again, theta I, theta R. Again, he says theta I is bigger than theta R, but now he's saying, that the velocity in water is much greater than the velocity of air. So he's saying that when light enters, a particle enters a more dense medium, it speeds up, where on Huygens' side, they were arguing that the velocity of air, the velocity of light in air is much greater than the velocity in water. So it's the first time we run into an opposite argument here. And the problem that stems from this is that the technology just doesn't exist that they can actually measure this. So Huygens, showing with the water table, showing the refraction pattern, being able to calculate or anticipate the direction, says that velocity of light in air is faster than water. On the other side, Newton postulates the only way for his theory of particles to work is that it needs to speed up, like going down a ramp, bending it toward that center line. So velocity of light in water is much faster than the velocity of air. So contradicting arguments, unfortunately, neither could be proven because the technology didn't exist. Who wins the argument at this time in history? Well, of course, Newton, because who is going to go against Newton? All right, Christian Huygens is a newer, younger scientist on the scene. Newton is a pillar in the scientific community, so no one's going to doubt his postulations. All right, so we'll pick this up in the next video.